All right, so we want to actually start with Kirchhoff's loop rule and Kirchhoff's junction rule. Those are going to be our problem solving techniques for getting the currents and ultimately the power in the bulbs. First, we have to guess. What do we think the direction of the current will be in each of the branches? Go ahead and make a guess for yourself, and then I'll put up my answers. Okay, so we all know that current likes to flow from positive terminal to negative terminal if we're talking about conventional current. So because we have a positive terminal here, it may be reasonable to guess that current will flow this way through R1. And we have a positive terminal here, so it could be reasonable to guess that I2 will flow counterclockwise in this section. But we also notice that the voltage that E2 supplies is substantially larger than the voltage of E1. And it's also possible for one battery to overpower another and push charge backwards through that battery. So we don't know for sure that our drawing here is correct, but it's okay if you guess wrong, because the mathematics will reveal if that guess was wrong later on. When it comes to R3, it's reasonable to assume that current flows downward through R3 because it wants to get back to the negative terminal somehow. Okay, so that's going to be our hypothesized directions of the currents. And it's okay if you had something different. The problem is still solvable no matter what you choose. Our next job is to use Kirchhoff's loop rule to write how the potential changes as we go around any loop in the circuit. Now, we could choose to analyze, like, what happens if we start here on the negative terminal and go around the loop, this small loop, and then we come back. I'm going to call that loop 1. And we could do a similar loop for the other side. It doesn't really matter which direction you go, but I'll start here and just go clockwise like I did before, but it doesn't matter. There's loop 2. Okay. If I wanted, I could make a third loop going all the way around the outside. And that could be my third equation. You need 3 equations to solve this. But I'm gonna write my third equation a little bit different. First, let's write the equation for loop 1. Okay, loop 1. Kirchhoff's loop rule says that the sum of all potential changes in the loop have to add to 0. So we want to first go through that battery. When we go from negative terminal to positive terminal, we're adding voltage though. We're going to go up 1.5 volts. So let's start with 0 equals plus 1.5. That's going to be our first change. Our next change though is to go through this resistor. And current flows in resistors from high potential to low. So the potential at this point in the circuit has got to be higher than the potential in this middle part. It's the only way that current could flow to the right. And we start with the assumption that our guess was correct, and we base all our equations on that guess, So if our guess is correct, then there will be a drop in potential, so I want to do minus something. And the thing that I put there, though, is not just like delta V of R1. I'd rather write it a different way. I'd rather write it as I1 times R1 using, Ohm's law on that element. And I'll even I'll even replace the R1 with what we know its resistance to be. Okay? Now there's only one more element to go through, and that's R3. Once again, potential is, we're going to be going from higher to lower is what's going to happen. And if we designate this as 0 volts, then technically this point should be at 0 volts as well, because they're in contact through a thick conducting wire there. So we're going to subtract I3 times R3, and R3 is 3.5 ohms. Well, let's write loop 2 then. For loop 2, I arbitrarily started at this point. We're going to be going through a resistor, but will we be adding potential or subtracting it? This point here I said was going to be at a higher voltage than this point. So we're actually going to be adding when we go through that element. So it'll be plus I3 times R3, which was 3.5 ohms. When we went down here and down in potential, I subtracted that term, but now that we're going up, I add it. And it looks like the same thing's going to happen here when we go through R2. We're going to want to add. Now we'll be going through this battery. But we're going through it not the conventional way. We're going through from positive terminal to negative terminal. So would that be an addition of voltage or actually a subtraction? It's a subtraction, right? Minus 3 volts. Those are our two Kirchhoff's loop law equations. And we just have to come up with one more equation. And so I'll actually use Kirchhoff's junction rule for that last equation. We see that I1 is heading into this junction here, and I2 is also heading into that junction. I3 is leaving the junction. Kirchhoff's loop law says that the sum of the currents coming in has to equal the sum of the currents going out. So our equation to write will be I1 plus I2 equals I3. All right, and those are the equations that we want to solve algebraically to get I1, I2, and I3. Okay, it was telling me that I1 equals 0, I2 equals 3/7, and I3 equals 3/7. And that's in amps. All right, so we want to check this and make sure that that makes sense and that that's valid. All right, so if I1 is 0 amps, that indicates no current through that resistor. And it's telling me that I2 is the same as I3. If that's the case, then when it comes to the power dissipated in R1, we have the formula power equals current times voltage, and if the current is 0, that means the power dissipated would be 0 as well. Okay. The power dissipated in 2 would be the current I2 times delta V2. So we're going to have 3/7 amps times the delta V. Now we don't know the delta V yet. We have to find it. Okay, so let's go ahead and call this 0 volts. Then this point up here must be 3 volts. This point would be 1.5 volts. If there's no difference across this, well, I should say, if there's no current flowing through that bulb, then this point would also be at 1.5 volts. And that checks with the Ohm's law. If you do the current 2 times R2, you get a drop of 1.5 volts in that resistor. So that's what we need here. So 3/7 times 1.5 gives us a power of 0.64 watts. And this one will actually match because we're going to go through the bulb, losing another 1.5 volts, same resistance. It looks like everything checks.